Okay, so let's talk about the 5.1. The topic is about the area underestimating uh, with the final sum. Okay, so again, guys, there are a lot of details about 5.1, 5.2, and even part of 5.3. The goal um, for me is let you to get some basic ideas about what's going on and then trying to link these ideas to what we learned from 4.8, the antiderivative, or the we'll also have a new name, the indefinite integral, right? Or integration. We'll trying to link them together, and 5.3, which talks about is definite integral, big part, and then 5.4, the fundamental theorem of calculus, another big part, okay? But 5.1 and 5.2, it works like a background introduction, where is this, the fundamental theorem of calculus from, where is, what's the meaning of this definite integral, okay? If we trying to present them in a different way. Um, okay, so let's look at one problem here, guys. So I have a function f(x) equals x squared, and I also give a closed intervals from 0 to 4, okay? And I plotted this function here, as you can see. Now this is my goal. I try to figure out the area under this curve, okay? Which, as you can see, is this part, okay? In this areas. But I don't know how to do that at this moment. And I would like to use some ideas to do one approximation first, And as you can see, we talk about this. If we have a giant piece, if we want to figure out either the volume or the area, remember the key idea is we split them into small pieces, right? And if we can handle the area for each small part, we add them together, done, right? So now let's look at this, okay? So trying to find one approximation. One way I can do is I can construct some rectangles, okay, to do the approximation. So this is what I can do. Okay. Now, the interval is from 0 to 4. First of all, I would like to partition my interval into two equal length interval, which, as you can see that, I'm gonna cut this, right? In other words, put a vertical dashed line through x equals 2. This gonna partition my interval into two parts, right? Each length is 2. Okay, each length is 2. Now, as you can see that I try to construct some rectangles to approximate the area of the under this curve. There's one way. What I can do is, as you can see, guys, I can use the right endpoint, the corresponding height, as the height of the corresponding rectangle. Okay, so you will see that from the first partition 0 to 2, what I can do is I can easily to calculate, the area for this rectangle, right? Now, similarly, as you can see that I can mimic the same idea, use the right end value, which is here, as a height of the rectangular. You can see that it is very easy to do the calculation. Agree, right? To do the calculation because the height for here, which is f of 2, the height for here, which is f of 4. So the approximation area approximation, do you agree, is the rectangular area 1 plus the area for the second rectangle. Now we can calculate the width, which is 2 for the first one, times the height, f of 2, plus 2 times f of 4, which we can do the calculation fairly easily. Okay, f of 2, which is 2 times 2 squared plus 2 times 4 squared. And as you can see, guys, you can calculate this part. This is 8 plus 16 times 2 is 32. So this area is 40. Okay, it's 40. It's not that difficult to do. In other words, I'm trying to use the area for those two red rectangles to do the approximation. But guys, you can easily see that we are actually overestimate the area, right? Because you can see here is the area that should not be under the curve, but we consider in. But also here, agree, right? Also here. So what we can do? Well, the idea is it possible we can make more partitions? Okay, we can make more partitions. Well, let's try to think about it in this way. Now I use a different color, the green color, to do the partition here. What if I partition my interval from 0 to 4 to 4 equal distance? In other words, this is how do I do a partition? Okay. Here, here, and then here. Okay. And I use a similar logic. Okay. Trying to use the height of the right end as a height for each rectangular. And then, let's see, I'm starting to draw this part. Okay. This part is the same thing. Okay, same thing. I just use a different color. You know, this two should be the same. Okay, just to make some notification here. Okay, and all right, guys. So, oops, I think let's take here. For the second part, you know, should be like this. Now guys, you can see that after I partition the interval into 4 parts, right? 4 equal lengths. Do you see that if I calculate the area for the first part, second part, third part, and fourth part, the summation of those 4 areas gonna have a better performance, right? Because think about this. Compared to the first partition, this part I didn't consider, okay? And also this part I didn't consider. So how do we do the calculation? Again, let's work on that. So if we call this is the first approximation, and if we call this is called the area APP2, okay, APP2, and that is the area 1 plus area 2 plus area 3 plus area 4, okay, which the length of the base this time is 1 instead of 2 because I partition into 4 parts. So it's 1 times for this part F1 plus 1 times F2 plus 1 times F3 plus 1 times F4. Okay, so you can easily to do the calculation, which is 1 squared plus 2 squared plus 3 squared plus 4 squared. That going to give us is, this is 5 plus 9, 14 plus 16, which give us is 30. Okay, 30. Guys, look at this. When we double the partition, okay, from 2 to 4, you can see that the area approximation, it actually increases dramatically, right? From before it was 40, right now it reduces into 30, okay? And do you agree that actually you can keep doing these things, right? Doing this repeat. I can partition it into 8 pieces, right? Agree, right? 8 pieces, and you know, to use a new board, as you can see, right? So look at this. So this is I don't know. So this is 1, 2, 3, and 4. Okay. So what we can do is we can partition them into 8 pieces, and this is what we can do, right? So here is 1 over 2, here is 3 over 2, here is 5 over 2, here is 7 over 2, right? So as you can see, okay, and you know, we can still continue to use the right hand side as the height, right? Right. And how do we calculate the area of those 8 pieces? Well, let's see. This is the area APP approximation 3, right? The third one, okay? Which is area 1 plus area 2, up to area 8, because we have right now we partition into 8 parts. And you can see, guys, right now the length of each base, which is 1 over 2, right? So it's 1 over 2 times f of half plus 1 over 2 times f of 1 plus 1 over 2 times f of 3 half, and as you can see, it's going to be 1 over 2 times f of 4, okay, f of 4. Okay, of course you can do the calculation, and by doing this way, again, guys, you can see that the approximation compared to the partition of the full parts, it will definitely be better. Okay, so every time we partition more, and it will be better and better. Then, so you can always continue, right, to partition into 16 parts, and then it will become better and better and better. But do you agree that you know, if I don't know, if we partition them into, let's see, 256, you know, intervals, and you will see that if you calculate those areas for 256 rectangulars, you add them together, and then if you double them, again, partition them into, let's say, 512 intervals, and then you add the area of those 512 small, super tiny, thin rectangulars together, you will see that actually the summation of the areas, the difference is already very minimal. And as you expect, guys, there's kind of like exists a limit. You know, no matter how large or how many partitions you go, and then the area gonna getting super close to the real area end of the curve, and you know that limit, uh, it is the area end of the curve. But meanwhile, we can use a notation to denote this. Remember, we talked about the indefinite integral, right? So this is what we call the definite integral. It has a lower limit, upper limit, function of the integration, and the variable of the integration. Okay, so this is called the integration of x squared from 0 to 4 with respect to x. And this definite integral, different with the indefinite integral, this gonna give you with a number, okay, instead of a function. And that number gonna be the area and of the curve. Okay, so right now there are some connections from here. Okay, from here. And about how do we calculate this, we're gonna talk about in another session. Okay, so I'll stop here.